Continuations represent an advanced concept and idea, and it is well supported in Scheme. In a simple case, continuations are used as an exit or exception mechanism, but there are also more sophisticated applications of continuations, such as coroutine sequencing. Let us assume that C is an expression in Scheme and that E is a sub-expression of C. The continuation of E in the context of C represents the future of the computation, which waits for and depends on the value of E. This may sound a little complicated, and in fact it is quite involved to really understand continuations. But imagine that we encounter E when we evaluate C. Then we are interested to capture the rest of the computation of C relative to the point E. This rest of future of the computation in C relative to E can be materialized as a function. So a continuation materializes the future or rest of a computation in C relative to E. In many respects, a continuation is a wolf in sheep's clothing, en ulv i fåreklæder, where the sheep is the function and the wolf is a continuation. Continuations become first-class citizens in Scheme because they are materialized as functions, and functions are first-class citizens. A continuation represented as a function always takes a single parameter corresponding to E. So given a captured continuation, it is possible to restart the rest of the computation relative to E. So we can store it away, or we could pass it to another point of the program. So from any location in a Scheme program, we can capture a continuation representing the future or rest of the computation, and we can treat this future of a computation as a function. So enough words and loose sketches. Let us give examples of continuations in concrete and small Scheme programs. Here, the blue stuff corresponds to a context, and the red spot corresponds to E, a particular point from where we capture a continuation. So what is the continuation of this point in the program? Well, in English words, the continuation of this spot is adding 5 to whatever value we have in the red box. Adding 5 to. And this continuation we can easily represent as a function. So this adding 5 to can be represented as this body in this lambda expression, and E corresponds to the red E in this context. Another example. What is the continuation of this spot in this context? Well, the continuation is consing 3, consing 2, and consing 1 to it. And again, we can capture the continuation as a function. So this idea of consing 3 to, consing 2, consing 1 is this body in this function, which represents the continuation of this point in this context. Here's a slightly more complicated example where we have the context C And the red spot E, what is the continuation of this red sub-expression in this context? Well, this is multiplying by x minus 1 and taking the remainder with integer division by x. There's no trace of the if in the continuation, because if either takes this way or this way early in the computation. If is a special form, if is the conditional expression. So when we are interested in the continuation of E, of the red spot, there will be no trace left of the if, because if is carried out early in the computation. So here we have it. The continuation represented as a function is this piece of program. Relative to the binding of x, it is multiplication and remainder. And E again corresponds to this part of our original program. So now let us illustrate how to capture continuations in Scheme in the read-eval print loop. We started with this expression where we were interested in the continuation of the multiplication. The way to capture continuations in Scheme is with use of a special primitive call with current continuation, which can be abbreviated with this alias. So this is a name of a special form, call CC. The full name is call with current continuation, but we usually use the abbreviation. So here is the way to capture continuations in Scheme. So this is syntax. This is fixed syntax for capturing the continuation, and the continuation is bound to the one and only parameter of this lambda expression. So E becomes bound to the continuation of this point in the program. E becomes the continuation adding 5 to. So in this example, we capture the continuation, but we don't use it yet. We will use it in a little while. But let us take the other examples as well. Let us capture the continuation of the empty list at the very end. And this is done here. So here we have the continuation, counting 3, 2, and 1, 2. And the final example, we capture the continuation at this point. And we have it here in E. So E is the continuation multiplying by x minus 1 and taking remainder. So we have seen that we can capture continuations, but not really disturbing the evaluation of the context. Now let us illustrate some simple use of the captured continuations. First here, we capture the continuation at this, in this way, and here we use the continuation. So we hand the value 7 to this point in the program, thereby obtaining 5 plus 7, the value 12. And in the second example, capturing the continuation here and handing the list of 4 and 5 to this point in the program, thereby obtaining the list of 1, 2, 3, 4, 5. Finally, we capture the continuation here and we use it here. So the value of this box becomes 3 because we explicitly give 3 as the starting point for the multiplication. 3 is multiplied by 4, giving 12, and the remainder by integer division with 5 is giving 2. Voila. Now let us look at some practical example in everyday scheme programming where we have a need for continuations. This is a list length function, and there are two cases. The length of the empty list is 0, and if the list is not empty, it is 1 plus the length of the tail. Let's try it out. List length of this list is 3, but if we pass an improper list, we will encounter problems, namely that we are taking the cutter of an improper list. So we want to capture this situation and be in control of the value returned from this case. Now, in some simpler Lisp system, we have primitives like cats and throw. Cats corresponds to try cats in other kinds of programming, and throw is throwing an exception. So it is a way to throw a value from here to here. Cats and throw is rather straightforward. They do not exist in Scheme because we can handle cats and throw with exceptions and call with current continuation. Let us see how it is done in Scheme. So this is a real Scheme program. We capture a continuation at the outer level of our function, and we define the recursive function at the inner level. So at the inner level, we have list length help, which takes the list parameter, and now we have 3 cases. The empty list case, as before, the case where we assure that we are working on pairs, that is proper lists, and if that's not the case, we have the exceptional case, namely we have encountered an improper list corresponding to this situation in our sample example. Now we activate doExit, and doExit is the name of our captured continuation. So what happens here is that we implant improper list as the value at this level. So in the situation we encounter the improper list, the simple improper list will be implanted here at the outer level, and we get improper list instead of an error. So let's try it out. List length of the improper list is the simple improper list. Now let us program a function that looks for a given subtree in this tree, which is a tree represented by an S expression, a tree that we have seen in one of the earlier lectures about S expressions. The function that we will program is here. It is called findInTree. it takes a tree and a predicate that is supposed to identify some given subtree in which we are interested. As in the earlier example, we capture a continuation at the outer level, and we name it appropriately, namely here found. So whenever we have found what we are interested in, we hand it to this continuation. Inside we have a local function called findInTreeHelp, which does the real work. It takes a tree and the predicate, and if we have found what we are looking for, we pass it to our continuation found. If not, we take the subtrees of tree, and quite imperatively, for each we apply findInTreeHelp on each of the subtrees. So now there are two cases. Either we find a subtree which we pass to our continuation, or we go through all the subtrees in tree and we never find it, and in that case we use the normal return, namely false. So in case we don't find any subtrees that fulfills the predicate, the result will be false. We miss this function, subtree list. We have to implement it, and it is here. At least it's here. Subtree list takes a binary tree, and if it is indeed a pair, we enumerate its two subtrees. If it's not, if it's a leaf, there are no subtrees. It's the empty list. So now let us look at an example. We, in SumTree, our example tree, we look for a subtree which is a symbol and which is equal to f. And well, we find f, and we just return it, as we see here. Could also be the case that we don't find it, and let's see what this would look like. Let's say we are looking for a number. There are no numbers in our tree, so we'll not find it, but we look for some number, and it's not there, and therefore we return false as an indication of we didn't find what we are looking for.